words under his shoe.
No, these are the first words in the string.
Huh? What? Okay, so now that we are starting to record, I'm going to ask one question, okay, because I'm on a committee, and there's this question of, when you're taking online classes, how many of you feel that there should be assessed, meaning graded, student-to-student interaction activities, like forums and discussion boards and stuff like that? So if you do not participate, you lose certain points. So what do you guys feel about it? As students?
I think it keeps you on your toes. I think it keeps you on your toes because every single online class I've had has done that.
Well, that's only because it's required. So the question is, should it be required?
For pure online classes?
Yes.
Yes.
It should be required? No? Yes?
So.
Depends on the class.
You need the more you
Okay.
keep your students engaged, the better. Because if you don't,
Right.
I don't think it should be required because it can interfere with your scheduling that you have to do to live your life outside of that. If you're doing an online class, you're already like barely squeezing for time, and you might not be able to get all the necessary interaction points that you need before a certain time period if your schedule conflicts with that.
Ah, okay.
So it would allow you to reflect your true academic ability.
Well, I have a different way to look at this. I look at it as every single online class should offer at least one way for students to interact with other students. Same thing as in the classroom, right? You guys are, I'm not putting, cones of silence around you guys. I mean, you can, if you have a question, you raise your hand and then you have the floor, man, go talk, right?
I think there should be like an open discussion like all the time for them to really just like.
Right, but should it be graded? Like, hey, you've been quiet for the whole class. I'm gonna take some points off.
I don't think it should be graded because, like, for example, like a lot of people that take online classes because it barely fits with their schedule and they can actually get to the work later on. Which is why that's like an important factor in the fact that some of them can't. Like he was saying, some of them can't get to it on time. So
right.
If it's gonna be graded, it should definitely be open to like where you can get back to it as long as you do it in some time. Yeah, that's like where the requirement should touch.
Well, there's one more. Yeah, go ahead.
Or like if someone actually gives out a very important tip or something for everyone that helps everyone. I mean, it could be like extra credit or something.
Okay.
Is it like time constrained or is it? I'm confused.
Well, they're usually time constrained, like within a certain amount of time. Not only do you have to post something, but you're also required to respond to somebody else's post.
So like a couple days or like a couple hours?
Usually in days.
Oh, then that's fine. Yeah.
Yeah, go ahead.
I think normally when I see those classes and the required posts, I see a lot of them just being like nonsense posts. People when they're seriously, when they're forced to do it, then they're just gonna not even think about it. A lot of people will, and that's another thing. Just because it's great, it doesn't mean you're gonna get valuable input from.
Doesn't mean it's going to be educational,
exactly.
Right? Yeah. So my take is, you guys know about ADA requirements, right? All the videos, they need to be closed captioned in case ADA is American Disability Act. And there are a few other standards too, but basically the bottom line is anything that is in a planned video, class recordings do not count because the actual presentation is right now, real time. So if there's a person here who is visually impaired, there will be another person here, doing the translation. Well, actually, a blind person can still hear me. Okay, but if someone has hearing impairment, there will be a person doing the signing and also typing the notes. So in the classroom, people with disabilities would get the help, like in real time. They don't have to wait. But for online classes, if your material is distributed through video, then the video has to be closed captioned because it has to provide equal access to all people. So my take is, if the distribution of material is, we focus so much on equity and everybody needs to have access, then when it comes to assessment, shouldn't we use the same philosophy and just say that, okay, the whole idea of your grade is to reflect your academic competency. But should we do it by, discussion boards? Should we do it by exams, or whatnot? And by putting the emphasis on interactive discussions, what about those people who are, for no fault of their own, autistic, and they just don't feel like, I don't want to post anything. right? I mean, so I think that's a little bit of a, irony, like contrasting quality there.
But there's only so much you can do in that case. It's so many.
Yeah, but some people are maybe autistic, but they can ace, math, physics, computer science classes. But if you say, but you have to participate in the discussion board, it really is the same. It boils down to the same thing as in the class. Okay, I point to a particular person and say, you have not talked for this entire class, and I'm gonna take points off. I don't think that is fair, because that has nothing to do with the academic competency of that person, unless that class is about communication. Okay, with peers, with other students. Okay, then okay, you're in this class. I have to assess it in that particular way. So that's just my take, but I do want to get your opinion as well, as students, because nobody asks you guys, do they?
No.
When they establish these guidelines for curricula and whatnot, do they ever invite students to go like, what do you guys think?
I have a biased opinion because I need participation in order to learn.
Exactly, but we all learn differently.
Yeah.
Some people do not like that. Some people would rather have some space, some time to reflect, just kind of some quiet environment to absorb the material. Other people would like to bounce off ideas, off of other people. The more they interact, the more they learn, or the more effective they learn. But we all learn differently, so that's the bottom line. They cannot just say that, okay, this is the style that people should learn, and we're going to structure classes like that. Okay, so that's good. It's all being recorded, but your names are not disclosed, so that's good.
They
You are-
find me.
You're anonymous.
This
Yep.
is Case Van Biden.
Okay, so how far have we gotten along in this particular module with memory devices, SR latch and stuff like that? I think I have presented a simple SR latch in
We
this
did the
case.
logism thing.
The logic same thing. Have we gotten to a D flip-flop? No?
We
Okay.
did the SR latch.
Okay, so we have done this one, and the next one is going to be the D flip-flop. So the D flip-flop, move, right here. Okay, there we go. So the D flip-flop is, I'm building the circuitry using this description here. So you can see that I'm not giving you a picture, instead I'm giving you some text. That looks like object-oriented programming in a certain way, right? And the way this works is I'm describing the components, and I'm also describing how the components are connected using this particular method. All right, so what we'll do is I'm going to look at this, and I'll be constructing the circuit on the side. So this way, when we're done, well, I suppose I can use LogicSim and do it at the same time. Okay, so what this is saying is we have a negation gate N. We have two NAND2 gates, N1 and N2. We have one SR latch that I just call SR in lowercase. We have two input pins. One is D and one is EN. D is for data, and then EN is for enable. And then we have two output pins, Q and NQ, which is kind of the same as the SR latch output Q and the /Q, the negated Q. And then over here we are adding nodes. Okay, each node is an electrical connection that connects multiple ports together. Okay, so in electrical term, D as an input pin, has a pin, which is the only port available on that device. N1 as a NAND2 gate has got two input pins. So I'm using the array notation to indicate this is attached to the first input pin, and this is the second input pin. And N itself, which is a negation gate, only has one input pin, and that's why there's no indexing for that particular pin. So are we okay in terms of what it means when I say, okay, we're creating a node to make connections between those ports of those particular components? Yes? Okay. All right, so we have 5 nodes, and I think I might have forgotten one, but we'll see. Okay, when we build a circuit, we'll actually check it out and see whether I'm missing something or not. And let's see, do I have LogicSim already loaded? Nope, not today. Okay, so that's easy enough. We just start up LogicSim. And I'm gonna have to flip and flop between the screens a little bit because I can't really see the other one. And I'm gonna do a little bit better because I already have one done. So I can pull the SR latch as if it is its own component. So let me go to, yep, this is the right one. So we'll right click, download, and I think I might have one already saved in my temp folder too. Yep, there's one already here. So we can just use that one. Okay, so if we go to open, there we go. So this is the SR latch that you are already familiar with. And I make the appearance to be just like that, okay? Your very simple 4 ports, okay? /S is the set port, /R is the reset port, Q is the non-negated output, and then /Q is the negated output. So the idea is Q and /Q should be opposite of each other unless both of the inputs are zeros. Then both outputs will be ones. Okay. So now we can make use of that as a component. And we're going to go to project and say add circuit. And we'll just call this a D flip-flop, DFF. And then we go back to the description on the web page. And locate the node here. I have it open somewhere else already, but this will work. Okay, so here's a D flip-flop. So we need 1 NOT gate, 2 NAND 2, 1 SR latch, 2 input pin, and 2 output pin. Okay, so let's pull all the components. 2 input pins, 1, 2, 1 negation port, or negation gate. So we get a NOT gate, put here. And I can name these things as we go. So this is our N. One of these is our data pin, which is D. And the other one is our so-called enable pin, which has the label of EN. And then we can go to the SR latch component, put one out. We call it just lowercase SR as the label. So the label is actually here. What else do we need? 2 NAND 2 gates. There we go. So we need NAND gates, but we need it to be 2 input. Make it a little bit smaller. Okay. And one is called N1. And the other one, oops, cancel. The other one is N2. And we have 2 output pins. One output pin is the non-negated output Q, and then the other one is the negated output NQ or /Q. Okay. And now we have all the components. Now it's just a matter of making the connections. So you can start anywhere, but having a particular order to do things might help. So I'm going to start with D. So we look up D.pin. It is connected to the first input of N1 and also the negation port. Now these are all connected in parallel. In other words, it's connected to all of these things at the same time. So we, just for graphical reasons, we're gonna put this one up here, and then we go through the negation gate like that. Okay, so that finishes the first node, this particular node, and we move on to the next node that connects EN to the other input of N1 and the first input of N2. So let's put it here, and just to make it look a little nicer, we can do it like this. Okay. All right. So we got these 3 things connected now, and then the next one is the output of the negated gate, or the negation gate goes to the input, the second input of N2. Oh, okay, I guess I kind of messed up here. Well, we can always take the scenic route. There we go. That is why I drive a Miata. Well, seriously, if I drive on Highway 5, I'm gonna doze off.
Street.
Yeah.
Superhighway.
It's got 2 lanes though. How's this?
And one out to SRS. Okay, so here we have the S here, and one to here. Okay, and an N2 to the reset. Okay, I did miss 2 connections because nothing goes to the output pins. So I'll just go ahead and connect Q to Q and NQ/Q to NQ. Okay. So I did miss 2 pins in the notes, but that's basically it. Okay. So we have the E because we basically simultaneously changed both inputs of the SR latch to from 0 to 1 from the perspective of the simulation. So it's okay. We can just change one of the states and that would change it. So go back to the poking tool. Okay, so now we're good. There we go. All right. So when you analyze this circuit, okay, you basically want to say, okay, what if En is a 0? What does it do to the rest of the circuit? So we are looking at it right now. En is a 0 right now. En goes to both gates unnegated, which means if En is 0, N2 and N1 are both guaranteed to output once. Because it's a negated AND gate, which means if at least one input is a 0, the output is guaranteed to be a 1. But if those are all 1s going into an SR latch, what does it mean to an SR latch when both inputs are 1s?
0.
Maintain state. Idle, do not change. Okay? And that's a reason. Okay, so let me ask you this question. Why do we have a slash in front of the S and R? What is the significance of that slash? Slash means negation, because in circuit description or pin description, a lot of times people don't want to use an overbar or the actual negation symbol, so they use a slash to mean negation. So in this case, the negation in front of the S means that particular pin is active low. Active low means if the pin has a 0, it means it's asserted. Okay, it's saying, okay, do that function. Okay, when the pin is high, it means do not do that function. Is that okay? Which is counterintuitive, but there are many circuits out there that have active low pins, for one reason or another. So in this case, the SR latch has negated S, or an active low set pin and an active low reset pin. So what that means is if those pins are 1s, it is not doing what the pin is supposed to do. Okay, set means making the output a 1, reset means making the output a 0. But if they're 1s, that means don't do a single thing. Okay, do not perform any function. Okay, so when En is a 0, you guarantee that the slash S and slash R pins are both 1s, which basically means don't do a single thing. The SR latch should not change its state. Is that making any sense? So at this point, I can flip the data pin up and down, and nothing is going to happen because of the N1 and N2 being NAND 2 gates. Is that okay? All right. So let me change D to a 1, and then we'll try to figure out what happens when I click on the EN pin to enable. What is going to happen?
It's going to turn off the top.
It's going to turn off the top, exactly. Because N1 at this point has one input being a 1 already, which is coming from D itself. So when En or the enable pin becomes a 1, then N1 is going to have both inputs being 1s, which means it's going to be a 0. The output of N1 goes to slash S, which means it is going to set the SR latch. When we say set the SR latch, it means turning the non-negated output to a 1. So the moment I flip En from a 0 to a 1, it is going to update the SR latch so that Q becomes 1. Okay? So we'll check it out and go, is that right? Okay, that works. So now the question is, what if I change D from a 1 back to a 0 without changing En? Okay, that's the question.
Change R.
So
into
if I change D from a 1 to a 0, then N1 is going to output a 1, which is basically just saying, stop setting the SR latch, okay? But just that is not sufficient to analyze what's going to happen to the SR latch. So the next thing we need to go is what if D is now a 0 going into the negation gate, and that goes into the N2 NAND2 gate. D1 becomes a 0. 0 comes out as a 1 from the negation gate going into the N2 NAND2 gate. So that means the N2 NAND gate is going to have two inputs, both inputs being 1s, which means its output is going to become a 0, which asserts the reset pin, which means the Q, non-negated output Q, is going to be a 0. We are going to change the SR latch to output a 0 instead of a 1. So we'll check it out and see whether it's going to do what I said it would do. And I misconnected something. Oh, right, I changed the wrong pin. There we go. Okay. There we go. So this is called level sensitive, okay? This D flip-flop is called level sensitive because what it's really saying is as long as the EN pin is a 1, whatever you present to D after a certain latency delay will be reflected to Q. Is that okay? And as long as EN is a 0, it becomes insensitive to whatever D is. So it's a level sensitive D flip-flop, which is kind of cool. How does this compare to a plain SR latch? What is the main difference between, from the perspective of the outside world, how is a level sensitive D flip-flop, how does it compare to an SR latch?
There's only one that you can change the whole thing, or the SR latch, it's both. They kind of interact equally.
I think I understand what you're trying to say.
Yeah.
With an SR latch, one pin is going to set the output, one pin is going to reset the output. So it doesn't really have one single pin to specify what the Q is supposed to be, and then the other pin to say, yep, go ahead and do it now. So with the D flip-flop, at least with a level sensitive D flip-flop, it is just like that, okay? One pin specifies what do you want the new state to be, and then the other one says, do it now. So that's why we have the enable pin. That is some rain.
I know. It's good. It's putting some water on this hill.
Yeah, well, it's even better for people who go ski and snowboarding, which I don't. I go down a hill with snow only one way, as a ball. Just stumble down.
French fry pizza, French fry pizza. Ready for the Olympics.
So is that okay? So are we okay with the analysis of this particular circuit?
So it's basically like the EN is like a write protection.
EN is kind of like a, for the lack of a better word, I know that word is going to be overused in this class. It's kind of like a gate. Okay, it's kind of like, well, if the gate is closed, it doesn't matter what you do on the outside, it's not going to change anything. So it's more like a gate. But later on, we have another way to describe it, and we'll get to that. All right, so if this is okay, this is a level sensitive D flip-flop. The next one is an edge sensitive D flip-flop, okay? And once again, we have a whole bunch of description here. This one is slightly more complex because you can see that it has two SR latches as its components. In addition, it has a 3-input NAND gate. In addition to a 2-input NAND gate, oh, this is a typo here. It has got 2 input pins. One is called clock and one is called data, or D. And it only has one output pin Q because I just completely ignored the NQ pin. I'm not bringing that out. Okay. So this one is done already. In this particular file, it is on the share drive already. You guys can just download it if you want to. So it's called a D flip-flop clocked. Okay.
Where is it in the share file?
Huh?
Where is it in the share file?
Circuits.
It is.
Circuits?
Yeah,
Thank you.
the circuit subfolder of the shared folder. Yep.
Thank you.
Okay, so this circuit is a little bit more complex, and the behavior is also kind of cool in a way. Okay, So let me just kind of move this one back a little bit because it's sticking out for no particular reason. Okay. And for those of you who are artists, you can complain about, how the wiring is unnecessary, twisted, and whatnot. It's called the Scenic Route. Actually, this one looks more like a parking lot Grand Prix, otherwise known as autocross. That's it.
Yeah.
Yeah. Poor man's race. Let's settle some cones.
Here we go.
I noticed the ARC parking lot is large enough for that.
It's large enough.
It's big enough.
Just dodge the speed bumps.
And this is the right weather to do it too.
It's true.
Yep.
You just get flat tires, little smooth tires.
Okay, so when we look at this thing, and the output is E only because, it's that's the initial state, so we just have to kind of make it not like that. Okay, there we go. All right, so when you look at this circuit, first of all, I'll tell you what it is supposed to behave, how it's supposed to behave, and then we'll analyze, how it accomplishes that. With this circuit, the state of the D pin, or whatever D is only used to update the SR latch called C when the clock pin is going from a 0 to a 1. Okay, I'll say that one more time. It is kind of like, in a way, like a level sensitive D flip-flop, except it only updates when the clock pin goes from 0 to 1. Only at that one instant it will update. After the transition from 0 to 1, you can flip D all you want, it doesn't change the output. When the clock is steady state, like a 0, when it's 1, it doesn't update the output either. The falling edge does not update the output either. It's only the rising edge of the clock pin that is going to cause the circuit to sample the D pin and then reflect the state of the D pin as Q of the SR latch called C.
When you say rising edge, it's when it goes from 0 to 1, right?
Yep, when it goes from 0 to 1, it's called the rising edge. Okay, so let's figure out how it gets exact, okay? Okay, first of all, now that the clock is at a steady state of 0, we want to say, okay, if I turn the D pin from 0 to 1, is it going to affect anything? Particularly, is it going to change the output? Okay, because we want to be convinced that when the clock pin is a 0, it should not do anything. Okay, the clock pin can be anything, but it should not affect the output. So instead of just clicking the pin and watching it change the state, we're going to walk this through mentally first. Okay, because that's basically how we study in this class, is look at the circuitry, look at the program, and figure out how it is going to get it done without running the program first. Okay? So when D goes from 0 to 1, what's going to happen? The NAND 2 gate connected to it is going to change. N2 is going to change its output from a 1 to a 0. Okay? And that's going to set Q. So Q is going to be set, which means NQ or /Q is going to be cleared. That 0 will come down here. And, okay, I'm missing something here. Oh, okay, so this becomes a 0, but so is the other one. So we have both inputs of the SR latch as being zeros. That's the one kind of strange state where both outputs would be 1s. In other words, the output of SR latch S is not going to change. If that's not going to change, then the rest of the circuitry is not going to change because the D pin is only connected to N2. And now we have come to the conclusion that the only one thing that N2 connects to, the output of N2 connects to, is not going to change its output. So as a result, the rest of the circuitry is not going to change. Is that okay? So now we have analyzed the case when the clock pin is a 0 and the D pin goes from 0 to 1, no change to the output whatsoever. Is that okay? All right. So the next thing we want to analyze is, let's change the D pin from a 0 to a 1, and you can see how the input here is now also becoming a 0. But having 0, 0 as the input to a SR latch is actually okay, as long as it is not followed by changing both inputs to 1s at exactly the same time. And then you can see how the Q is a bright green dot, which means it's a 1, and then slash Q is also a bright green line. So when it gets to the SR latch called C, that's just maintaining state. It's not changing anything. So now, what happens when I click on the clock pin? In other words, what if the clock pin is going from 0 to 1? So we want to analyze that particular moment.
Nothing will change.
That's when it starts to click. That's when it records.
Supposedly, yes. But we want to analyze the circuit and find out how does it get it done, okay? How does it capture just that moment, okay? So when clock goes from 0 to 1, this line, okay, let me just highlight, this is the other thing that I really like about LogicSim, is when you click on a particular node, every single wire connected to that node is highlighted. So that makes it easier to identify, okay, what are we analyzing? That is what we are analyzing, okay? So what if this thick line is going from a 0 to a 1? That is the question. First thing is going to be, we can look at this SR latch S here. We will have the slash S continuing to be a 0, but slash R is now going to be a 1, which means it is going to set the Q pin, which also means it's going to flip the slash Q pin to become a 0. So when you follow this wire, this pin is going to be a 0, which means we are setting the SR latch called C, which means Q is going to update to a 1. Okay? But it also connects to N2. It doesn't do anything to N2, because N2 has another wire that is still going to be a 0.
N1.
So N2 will continue to output 1. I mean N1, sorry. So N1 will continue to output 1 because out of the 3 inputs, this wire, the last one, continues to be a 0. Is that okay? But the conclusion is it's going to change the SR latch C and change our output from a 0 to a 1. Okay, so we'll do that. Click, and it changes. But I'm claiming that at this point, even though clock is 1 at this point, I can flip D, any way I want, and it's not going to affect the output Q of the overall circuit. So in other words, if I change D from a 1 back to a 0, what's going to happen? Let's try to figure that out. So we're changing D from a 1 to a 0. So the first thing it's going to affect is going to be N2. N2 now has one input being a 0, which means its output is going to be a 1. So now we have 1, 1 to become the input of the SR latch S. What is the 1, 1 configuration going to do to an SR latch?
Idle.
Idle, maintain current state, which means the rest of the circuit is not going to change anything. It's not going to experience any change. And that's it, because once this wire is not changed, there are no additional changes because of changing D from a 1 to a 0. So now that we kind of predicted the behavior, we can now go ahead and click it just to verify that that really is the case. Is that okay? So that's kind of cool, because now that it's not level sensitive anymore. It only captures that moment when clock goes from 0 to 1, then it captures whatever is presented at the D pin and reflected at the Q pin, of the entire circuit. Is that okay? All right. So if I want to change the output from a 1 back to a 0, let's see what happens when I have a falling edge on clock. Okay. In other words, is it sensitive to the falling edge? We know it's not. Okay, but we want to analyze the circuit just to understand why it is not sensitive to a falling edge on the clock signal. So clock is now going from a 1 back to a 0. Let me highlight the node so that we know which connections we are looking at or we are focusing on. That becomes a 0, which means we are going to reset the output of the SR latch. If we reset the output pin, it's going to set the negated Q pin, so that becomes a 1, and so the slash S signal of the SR latch C is going to be a 1.
Maintain current state.
Okay? well, we have one more wire, so we got to look at the other wire. So the clock is also connected to one of the input pins of N1, but because the other input pin of N1, oh, that's going to change at the same time, because this is going to be a 1, which means this is a 1, but clock itself becomes a 0, right? So we still have at least one input of N1 being a 0, which means N1 continues to output a 1. So that means, as far as at the SR latch C is concerned, both inputs would now be 1s. And once again, what does that mean?
Maintain state.
Idle, maintain state, do not make any changes, right? So that means the output of 1 from SR latch C is going to still continue to be a 1. Okay, so we click this and go like, oh, okay. Oh, I clicked it one too many times, darn it, okay. Okay, now I have to reproduce that condition. Okay, there we go. Okay, now, so now that the output is a 1, I want to flip it back to a 0 by a rising edge on clock. How does it get it done?
Switch clock back to 0?
We're switching clock from a 0 to 1. So once again, we have a rising edge, which means the circuitry is supposed to sample whatever is at the D pin, then reflect it over at the Q pin.
If you turn clock back to 1, it's not going to change SR, but it's going to turn N1 off.
It's going to, exactly, so this wire is not going to do a single thing, so SR latch S is going to maintain its output. So this is not going to change. On the other hand, when you have a 1 presented here, then N1 now has all 3 inputs being 1s, which means its output is going to be a 0. That 0 is going, so we have to track on both connections. The first connection is not going to do a single thing, because N2 already has an input being a 0. Having 2 inputs being 0s doesn't change it at all, doesn't change the output of N2 at all. Is that okay? But how would it change, how is that going to change the second component, the SR latch called C? It's going to reset the output of SR latch C, which means the output is going to be a 0. In other words, it captures the input pin called D and reflect it as its own output. But we're going to do it. You just click it, and you can see how it is now, the output is changed to a 0. Is that okay? So I personally think this is quite ingenious. Okay, I probably cannot come up with something like this. But then again, my degree is not in electrical engineering, so I'm not experienced in analyzing circuitry like this or figuring out how to perform something like this. But whoever came up with this, I think is pretty ingenious. Okay, because it's really kind of cool. All right, so this is called a clocked or edge-sensitive D flip-flop. You can use either term. Okay, clocked simply means it pays attention to the clock line, and it implies it is edge-sensitive. And obviously, the word edge-sensitive applies to the clock line. Yep.
So just to clarify, the rising edge of the clock replicates whatever D is set at to Q?
Correct. At the moment of the rising edge,
only at the moment of the rising edge.
Only at that moment,
okay.
Right. So right after that moment, you can change D pin all you want, and it doesn't change the state of the D flip-flop itself. Okay, so we go back to the notes, and there's another one, the next one. So this is my analysis, just kind of put into words, but it's basically the same exercise that we just went through. So you really should read this and understand what it means, because it's just a repetition of what I said earlier, but just put into words. Okay. So the next one in section 6 is called a clocked and gated D flip-flop. And this one is kind of interesting because now we have 3 inputs, 3 SR latches, and the whole thing gets a little bit more complicated. So I'm not going to emulate this particular circuit. Okay, I'll leave it up to you guys to do some analysis. This slide I just added it yesterday, okay, because during the explanation to the Tuesday, Thursday class, it just occurred to me, hey, I can explain, each input pin in this way. Okay, we'll start with the obvious, okay? Data is specifying how we want to update the output of this entire circuit, okay? Are we changing it to a 0 or are we changing it to a 1? So that's what the data line is doing. So it is specifying the what. What is the new state? En is kind of mysterious, so we'll talk about En later. Clock specifies when, because the moment of the rising edge is when we want to update the output of this entire circuitry. En is specifying who or whom, depending on the sentence structure, but it specifies who should be paying attention. To understand why we need these three particular things, without talking about the process or architecture itself, we can just kind of look at it in a class setting, okay? Or we can look at it, we'll look at it from an orchestra perspective, okay? Because we'll use that analogy again and again. So the components inside the processor is kind of like individual sections of instruments in an orchestra. Not an individual instrument, but an entire section, okay? So you might have two groups of violins, two groups of flutes, one group of trumpets, and so on and so forth, okay? So the conductor, there's only one person, right? The conductor is keeping track of the beats for the entire orchestra. So that means the entire system, okay, the entire processor only has one single clock. Is that okay? There's only one clock for everything inside the processor. The clock line goes everywhere to every single component that needs to be synchronized. So everybody's paying attention to the conductor, doing the thing, right? Using the baton and stuff. Data is basically the facial expression on the conductor. Okay? How many of you have gone to a concert, or have watched a concert with an orchestra? Okay, most conductors are pretty expressive, right? They're called maestros for a reason. Okay, so they're pretty expressive, and their expression is data. Okay, it's telling the string section to be, and it wants the flute section to be louder, and so on and so forth. That's data. Okay, but if the conductor just do like this, the entire orchestra is going to quiet down, because everybody's paying attention to the conductor, right? And that's not what the conductor wants. The conductor only wants, an entire, just one section, softer, and in some cases, just one place, like that, right? That's your enable. Each device inside the processor has its own enable. The data line is still shared. The clock line is definitely shared, but the enable is individual. So by controlling the enable, the conductor now has the ability, the processor, the core part of the processor, can now specify, you go ahead and update. The rest of you do not update. And it can also specify when to update because of the clock line. And then how you're going to update it is controlled by the data line. Now the data line is not always connected to every single component. The output of one component can become the input of the next component, and so on. So are we doing okay so far with this circuitry? Yes? Okay, cool. And there's one more. This one has got 4 pins. So the extra pin to this one is called the reset pin. Okay, this is the extra pin here. So we can kind of look at the reset pin and see what it does, right? So the reset pin doesn't do much. It is going straight into this OR gate here and also this AND gate here. So the effect is, because it is, this bubble means it is negated. So if the reset pin is a 1, is a 0, it is ORed, it becomes a 1 right before the OR gate here. What does OR 1 do in general? or in a logic expression, what is or true going to do? Doesn't do a single thing to the output. Let me see. This one, I think the reset is actually negated. It's an active low pin. Let me read this part here. It is active low. Okay, so it is active low, which means under normal circumstances, the reset pin is going to be 1. Okay, so forget what I just said a little bit earlier. The reset pin is normally a 1 during normal operation. So that 1 becomes a 0 presented to the OR gate. What does OR false going to do? Something OR false is that something, okay? Because anything OR 0 is the original thing, okay? So that means when the reset pin is a 1, it doesn't really do a single thing. We might as well just draw a straight line through here. What about AND? When the reset pin is a 1, it is non-negated to A3, which means we're talking about something and true. Something and true is the something. Okay, the 1 is the identity of conjunction, so something and true is just that original something. In other words, when the reset pin is a 1, it is as if A3 is not there. It is as if the other input is connected straight to the output. Is that okay? Mm-hmm. What happens when reset becomes 0? When reset becomes 0, the negated 0 becomes a 1. So this OR gate is guaranteed to output a 1. And that 1 means we are not setting the SR latch. Is that okay? What about the other AND gate, this one here? When reset is a 0, we only need one input to be a 0 for the output to be a 0. This is a regular AND gate, it's not negated. So the 0 comes out here and it connects to the reset of the SR latch here, which means the output would become a 0. And this is all regardless of the rest of the circuitry. You can specify anything you want as far as clock, enable, or data is concerned. When the reset pin goes from 1 to 0, the state of the entire D flip-flop goes to 0. Is that okay? Why do we need that pin? Why do we need a reset pin? And by the way, the reset pin is also global. The entire processor and most components inside your computer, they all share the same reset pin. So why do you think there's a necessity for a reset pin?
So you can turn it off?
Not turn it off per se.
To
So that everything,
reinitialize it?
yeah, go ahead.
To reinitialize everything?
To reinitialize, yes. So everything can go back to a default state, to a known default state. When do you need to assert the reset pin? No.
Something goes wrong?
When something goes wrong, okay, what kind of thing do you think that might be?
Virus?
Okay, that's not incorrect, but how is a virus going to trigger the reset pin?
You want to erase the memory?
It affects memory. A virus would definitely do some strange things to the memory and the operating system.
Like a hardware reset?
A hardware reset, exactly. Okay, so we have a software issue. How does it lead to a hardware reset? That's the next question.
When things go really, really, really bad?
Loop or something? Like if you get into some kind of loop that you can't get out of software-wise, you're gonna have to do it.
Yeah, something crashes.
But how does your computer know that it's in trouble?
Because it's using a lot of processing power, not getting anywhere?
But how does it know it's not getting anywhere? That's okay. I mean, you guys are not supposed to know, so I'm just prompting you guys to kind of think about it. Okay, it's called a watchdog timer. Okay, you can look at that word. It is it's the name of an actual device on most things that are electronic. It's called a watchdog timer. So what a watchdog timer does is, so the watchdog timer is connected to the reset line. Okay, along with many other devices. So the reset line is shared. Because the only thing, it's basically held high through a resistor. Anything that can drive it down, drive it low, can make the reset line low. So there are multiple sources that can basically cause a reset on your computer. One of those devices is called a watchdog timer. So the watchdog timer is holding onto the reset line, ready to pull the voltage down, but it will only do that when the watchdog circuitry's timer expires. Okay, so think of it like this. Okay, think of it like I have a little kitchen timer thingy. Okay, so I set a time to 3 minutes. Okay, if someone quote unquote hits me, okay, that's how we call hitting a watchdog timer. So if someone asserts me and say everything is fine, I'm gonna reset that timer back to 3 minutes. Do you guys see what is happening?
Mm-hmm.
So I have a period of 3 minutes. If you assert me within 3 minutes that everything is cool, I'm gonna reset that timer back to 3 minutes. So you have another 3 minutes to assert that everything is okay. All right? So this is how your Windows, Linux, Mac OS X, all the mobile devices, they all operate about the same way. So your operating system has a timer. We'll talk about this later, but it's called the ISR, or interrupt surface routine, that will basically hit the watchdog or assert that everything is cool every once in a while. Okay, so the watchdog timer keeps resetting the time, and it's not gonna reset the whole thing. Now, when your computer is either infected, or it has a driver issue, or there's some other issue that's causing that assertion not to happen, then the timer of the watchdog is gonna go off, right? 3 minutes is up. Nobody told me that everything is cool. I'm gonna assume something bad has happened. Okay? And what do you think the watchdog timer is gonna do when it thinks something bad has happened? It's gonna yank on the reset line. The reset line goes from 1 to 0, and what happens then?
Everything resets.
Everything resets. So it is as if you just rebooted your computer.
So is that pretty much the blue screen that in terms of Windows?
Almost.
Every time I start a
Okay.
Bethesda game.
So the reset line, if the watchdog timer is connected to the reset line, then it would just be your computer resetting itself or rebooting, but it won't give you the blue screen of death.
Okay.
Okay, the blue screen of death is only happening because the watchdog timer is not connected to the reset line on a normal PC. It is connected to what we call an NMI, non-maskable interrupt. Okay, which basically is a way to get the processor's attention, and it cannot be masked, cannot be ignored. Okay, so when that is asserted, then your processor go like, oh, something bad has happened, and then it will go to what we call the NMI handler, which is a section of code in your operating system that says, okay, in case of emergency, do this. And that's your blue screen of death. Because the blue screen of death is valuable to developers. It gives the developer a point in time when the developer can say, okay, dump all 16 gig of RAM onto the hard drive, save everything. So then the developer can do a post-mortem analysis of what program is running at a time, what devices are attached at a time, and so on and so forth, to try to find out what caused that problem.
So that's why it asks you that, whenever it crashes, it asks you to send a report to Google or whatever.
Yep. Now your mobile device may be different. So your mobile device doesn't give you a blue screen of death. I mean, as far as I know, Android devices do not have a blue screen of death. When they reset, when something bad happens, it just reboots. So that tells me that in the case of an Android device, the watchdog timer connects straight to the reset pin instead of the NMI. Is that okay? What else do you think might cause a processor or a computer system to say, oh, bad things is happening, we should go back to the default state? Heat will cause your operating system to reduce the clock rate until it is safe, or it will just kind of shut down. What do you think is a brownout? We know what a blackout is, right? Somebody, a pole just went down and then you lost power entirely. That's a blackout. What is a brownout?
Isn't that dirt?
You get partial power.
You get partial power. Very good. Okay. So when a transformer starts to go, it will give you a brownout, because you still get some voltage on the line, but you're not going to get all the 110 volt. You might get like 50 volts, 60 volts, or something like that. It might even go up and down a little bit. But as far as this power supply of your PC is concerned, that is not good. Your processor is not going to get the full voltage that it needs to operate safely. So that goes to another chip called a supervisor chip, and it monitors the incoming voltage. When the incoming voltage is dropping below a particular threshold, it holds the reset line low. It's basically saying, until the voltage is safe again, I'm going to hold everything. I'm going to halt everything, and everything is going to go to the default state, which should be safe. So that's why we have a reset connected to everything in the computer. So is that okay so far?
So what's this one called? A resettable?
This is called a resettable gated edge sensitive D flip-flop. So let's go for the pins. It is edge sensitive, gated, and resettable D flip-flop. That's one bit. This is how you store a single bit. So now the question is, then how do we store multiple bits? This is how you do it.
Jesus Christ.
Now, Jesus has nothing to do with this. Trust me.
It was John Von something.
John Vonneman. No, he probably has nothing to do with this. This probably existed before him, because even computers before him, they have to store data. So this is how we store multiple bits of data. You can see that we have one single clock. Okay, so clock is coming in. It connects to every single edge-sensitive, gated, resettable D flip-flop. Okay, each one of these can only remember a single bit, but that's okay. We have the D pin, but this time the D pin is an 8-bit pin. We use a splitter to split it into 8 different outputs, individual bits. You can see how this is getting bit 0, this is getting bit 1, bit 2, and so on. Okay, so each one is getting a different bit. Enable is shared in this case. So enable is just shared between all the devices. When enable goes to 1, we're enabling all of those single bit D flip-flops. Is that okay? The clock line is shared, and the reset line is definitely shared as well. So the reset line is also shared within all of these D flip-flops, single bit D flip-flops. And then the output of the D flip-flops go through a merger, which is basically a splitter in reverse, to the output pin Q. So this is how we implement a multi-bit, what we call register. A register, R-E-G-I-S-T-E-R, is basically a multi-bit D flip-flop. You tell it what to remember, when to remember, and who should pay attention, and it will get the job done.
So is every bit in D is being paired with every other bit at least once in one of the gates?
Every bit in D.
In D, because it's going split 8, and there's 4 inputs and eight gates. So each bit is being compared with every other bit at least once.
Not compared.
I mean, going through those gates at least once.
Each bit goes to a specific bitwise D flip-flop.
It's not all of them.
That is correct.
Oh, okay.
So when you look at bit 0 only goes to this single D flip-flop. When you look at bit 1 only goes to the second D flip-flop, and so on. And then the output is the same way. The output of the first D flip-flop becomes bit 0 of the merger. The output of the second D flip-flop becomes bit 1 of the merger, and so on.
And what's the fourth part? If one's clock,
What do you mean fourth part?
Because there's 4 inputs.
This one?
Yeah.
That's the reset.
Oh, the reset. Okay.
So the reset is they're all connected together, because if all the registers of the entire processor, they all connect to the same reset.
All right. So you basically do it 8 times.
Yes. Yep. The only thing that is on a per D flip-flop basis is data. Everything else is shared.
Huh.
Is that okay?
Yeah.
So this is the simplest, quote unquote memory device inside the processor that actually is useful to us. You can pull an SR latch, from Logisim. It's not going to do us a lot of good in the design of a processor, but a register does. So we doing okay so far with the explanation all the way up to here. Okay. So we have talked about a lot pine needles today. Okay, so we are basically looking at the pine needles and go like, look at this pine needle, it's really cool. Look at that pine needle, it's really cool. So it's time to kind of step back and look at the pine tree, right? So the pine tree is basically asking the question of what have we been talking about today? Well, the entire discussion today brings us to this point, okay? How do we come up with a device that can remember a binary number? Multi-bit binary number. This is how we do it. We take another step back and then we look at the pine forest, right? So the pine forest is pointing to the direction of, okay, so if we zoom in, okay, so which means in this case we are going back in time. So we zoom into this picture and we look at one of these things called the SR latch. So we look at the SR latch, goes all the way to the beginning.
No, it's not much.
It doesn't have a picture, but it has a description. But it's made out of NAND 2 gates, right? And what do you think NAND 2 gates are made out of? 2 N transistors and 2 P transistors, right? So it boils down to the fact that, registers can be done with transistors. So that's the pine forest that we are looking at. So now that we have a basic circuitry that can do adding, and a basic circuitry that can remember things, right? We can now start to do something that's kind of cool, called a counter. Okay? Let's figure out what a counter is. Okay, that's actually not in the notes. All right, so I'm going to pull the actual register as a component, so I'm not going to make my own register here. But we'll make a new circuit, and we'll call this counter, okay? So as I said a little bit earlier, a counter has a register, and a register is under memory. Okay, so you can look at all these. It has a D flip-flop. We don't want to deal with a D flip-flop. We just want to register. So here's a register, and we also want an adder. Okay, and we're not going to use our own 3-bit carry log-ahead adder. We're just going to pull the component from arithmetic, and just pull an adder here. Okay, so the first thing is to explain what are the ports of a adder, what are the ports of a register. So with an adder, this pin is carry in, which is the same thing as our K0. This is X, this is Y, this is carry out, which in the case of a 3-bit adder is K3, and this is the result, which in our term is S for sum. Is that okay? So 5 ports for an adder, and then for the register, this is D, which is the same thing as our D pin. Q is the same as our Q pin. One is input, one is output. This is enable, which is the same as our enable. This is clock, okay, except it is not spelled out as CLK. Instead, it has a little kind of triangle symbol, which I think is industry standard for certain manufacturers, but not all manufacturers use this particular standard. And this pin is labeled 0, which is a reset. Now this reset is not active low, it is actually active high. So it's opposite to how I designed the circuit earlier. Okay, so now that we have this component, we want to make a counter. Okay, we want to make a counter that keeps incrementing until it overflows and then start from 0 and go again. Okay, that's a very, very basic counter. It just adds 1 to itself, and then it goes through that whole cycle again, add one more time, and then add one more time, and keeps adding. Is that okay? All right. So the question is, how do we make it happen? All right, so the first thing is we want to add 1. Okay, this is a full adder, which means you can specify any number, as Y. You can also specify, K0 or carry in, as a 0 or 1. You just need one of these things to be a 1. It doesn't matter which one. Okay, so I can pull constants out of wiring to make certain things constant. So let's see, constant is,
Right after clock.
huh? Okay, there we go. So we can make y a constant of 1. It doesn't like it because this is a single bit, so we want to increase it to the same width as our adder to be 8 bit wide, and we want to add 1, not subtract 1. So we want to specify this to 0x01, which is hexadecimal 1. With this being a 1, then the carry in can be a 0. So we pull another one of these constants and change this one to 0, the constant 0, so that we have carry in being 0 itself, and we can ignore carry out because that's not useful for whatever we are doing here. So now the question is, how do we wire up this thing? So the output of this goes to the input of the other one. I think that's kind of makes sense, right? So the output of this goes to the input of the register, like that. And the output of the register, in return, becomes the input of the adder. Okay. Oops, too much. Like that. There we go. All right. We are not going to connect anything to the reset. In fact, we'll just get a 0. So we're going to share this 0 with a bunch of pins here, which we basically say, let's not do anything here. We do want the enable to be a 1, because otherwise it's not going to pay attention at all. So we want a 1 to basically say, always pay attention. There we go. Huh?
Isn't this going to be a loop?
It is a loop. However, it's an interesting loop. Okay? Okay, so up to this point, it is a loop, and now the question is, okay, I can see that the output of the register becomes the input of the adder. So this is going to do the adding. So when you poke this wire, okay, let me poke some wires so that we can see what is on each signal. Okay, so when we click this one, it's going to be 0 because it's coming from the register. The register currently has 0, 0 in hexadecimal, which is basically 8 zeros in bits. Okay, which also means the output of the adder should be 1 because 0 plus 1 is 1, and we can click it and it confirms that it is 1. So, but how come the register is not getting changed? The register is doing like, nope, not going to do anything because it is edge sensitive.
Oh.
And no one, the clock line is not even connected yet. Okay, so it's not going to do anything. So what we'll do is we're going to pull a pin. It looks like a pin, but it's not a pin. It's called a clock. Okay, so when you look at a clock, it resembles a pin in the same in terms of shape, but it has this kind of like a square wave thing inside, which means it can be automated. You can click it if you want to change its state, but you can also go to simulate and make it clock automatically. An input pin cannot do that. Okay, an input pin has to interact with someone, but the clock pin can automate. Okay, but we're not going to automate just yet. Okay, we are going to do 2 output pins because we want to monitor the output of the adder and the output of the register, so that we can actually see the whole thing happening.
Every time you click the clock pin, it's going to increment by 1, isn't it?
Only on the rising edge. Okay, so we connect it here, like that. Control D, which is duplicate, and then we connect the, oops, up, here we go. Okay, that's going to be a 0. Okay, so at this point the clock is outputting a 0. When I click on when I use the poke tool to poke the clock pin, it's going to alternate to 1. So when that happens, whatever is presented to the input of the register is going to update the output. So when I change the clock pin from a 0 to 1, the register will be updated to 1, okay? And it's going to change its output to 1. That output in return goes to the input of the adder. The adder is not a clocked circuit in In other words, there's no clock pin going into the adder. The adder changes its output after a certain latency according to its input. But LogicSync doesn't, it's so fast that it's instantaneous to us, okay? So the moment the input of the adder becomes a 1, its output will become a 2, and then it stops. Because the clock is now a 1, which means the register is not going to pay attention to the 2, which is coming out of the adder. So this Y will be a 2, but the register is saying, I'm not going to change anything, because I'm not seeing a rising edge on the clock pin. So then I can I can change the clock back to a 0. It becomes a falling edge. Falling edge doesn't do a single thing to a register, okay? And then when I change the 0 back into 1, then we have another rising edge. Then the register will update from 1 to 2. Is that okay? So every 2 clicks of the clock pin will update the register once. Because each click of the clock pin is 1 edge, but you have to remember that we have a rising edge and then a falling edge, a rising edge and then a falling edge. There's nothing being done with a falling edge, only with the rising edge. Okay? So we'll go ahead and observe this. Okay? The first few times is really fun, like this. See? Update, 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 and then the 5th time is really boring. So if it is too boring, too much to you to kind of click, because you have a $200 gaming mouse and you don't want to overuse the mouse button,
I got a million clicks we talking about.
then you can go here and you can specify the click frequency. I would suggest something that you can actually see. In other words, go down to maybe 4, 4 to, that should be okay. So 4 hertz is 4 changes per second, which means every quarter of a second there will be a change. So that should still be visible. Okay? We can actually see it. We may not be able to count as quickly, but we can see it. Then you go to simulate, and then you just say click enable, and you can see how it's automatically updating itself. So that's a counter. A very, very simple circuit. But now we can make a counter. Only now we have the necessary circuitry to make a counter because of the register. Before we have the concept of a register, we have an adder, right? No problem. But how do you get the output of an adder back to the input in a way that it doesn't keep doing that?
Out of control.
Yep. But now we have control over timing. We can say, yep, update, update, update. And in between the updates, maintain state.
Is this like a clock then?
Yep. It's kind of like a really, really basic clock.
Huh.
So I do need to specify one thing. When it specifies the frequency here, that is actually not correct. The actual frequency is whatever it specifies here divided by 2. Because it's basically saying we're clicking the clock pin. That doesn't look like 4 times per second to me.
It's 2 times a second because it's every other.
Yeah. Yeah, it's almost like only twice. So I think that clock rate is not entirely correct.
Well, it's just every time it clicks. So you click it to turn it on, you click it to turn it off. That's 2 just to make it turn once.
Well, but it's not the duty cycle. Oh, okay, I see. Now it's the same duty cycle. When I hold the mouse over this, you can see how it changes the duty cycle. Like the amount of time that it stays on and the amount of time it stays off is not even anymore. Now it's even. Okay, so if this is really boring, you can always crank up the tick frequency to something that is barely registering to the human eye.
No, 41, go. It's all or nothing.
Yeah. Or you can make it go so fast that you cannot keep up.
There we go.
Unless you have a
No,
gaming
wait.
monitor.
4.1, do it!
Unless you have a gaming monitor and you are fly.
Break the computer.
So now you can go to your parent and say, I need that, $600 gaming monitor because I need to keep track of all this stuff. I can watch it happen.
I need more processing power.
What is the refresh rate of a gaming monitor?
144.
144? I thought the human eye can only register changes up to like 30 frames per second.
But you could feel it.
That's what people say who haven't seen a gaming monitor.
Yeah.
Okay. So with a gaming monitor, you can actually see smoother.
Yeah.
The main
updates.
difference is when things are moving. Like if you try to
Yeah.
read a sign when you're moving, even at 60 frames, you can't do it.
Oh, so your eye can actually register
Change.
changes faster than 60 updates per second. Interesting. But even that is not very high compared to flies.
Mhm.
Yeah.
Because flies can. Okay.
360.
Now you got me curious.
The trick to killing flies.
So
is
we're gonna look it up. Okay. So we're gonna look up the refresh eye flies. Okay, that should be enough. Time doesn't fly if you're a fly. Okay, so the fly's eye update its brain far more frequently than ours, but it doesn't. Okay, maybe it does say what is the frequency, but I know it's really fast, to the point that your fluorescent light to us is constantly on. The flies would actually see on, off, on,
Oh, the Daily Mail.
off.
That's totally legit.
It's the same with dogs on the TV because the refresh rate on the TV is too slow for a dog's eyes. So to them it's like it's flashing. It's obnoxious to them.
Okay, did I spell
Yeah.
frequency?
I've actually seen dogs watch TV.
Yeah. They do it because you do. They're very sensitive to
Okay.
emotions.
Okay, it says much higher,
Unless you get a
but no actual number. Alright?
I gotta get a gaming monitor so my dog could watch TV.
Hey man, I looked down and found one on sale.
Hey, if you want your dog to watch TV, you can get a black and white.
That's true.
There we go. 300 frames per second for dragonflies.
Is it 14?
Huh?
It's important to know.
But that's why insects can evade our hand, pretty quickly. Like, if you try to hit a fly using only your hands, it's to the fly it's all in slow motion. It's like, yep, the hand is coming.
I
Okay,
think I'll move later.
I'm gonna slurp some more of this stuff, right? Oh, it's the hand is still coming. I think I can slurp, and one more time. Okay, I guess I'm gonna back off a little bit now. To the fly, it's all slow motion, even though to us it's really fast. Now, rubber bands, on the other hand, is a different story.
Rubber bands.
That's how I get my flies. Yep, you use like 5 or 6 rubber bands, so it becomes a rubber band shotgun. Yep, it's super effective
No, you gotta
because
cut
it's
wood.
not a single point; it's a cone. It's a cone, and I think one time I hit a fly like that, and over the next 3 years, I keep finding parts on my desk. Oh, here's a little antenna. There's another leg over here. That's exactly what a shotgun would do to a fly.
Obliteration.
Yep.
Fire
And it's
that.
rubber bands. Yep. So are there any questions about this stuff? Not the fly or dragonfly.
Oh, not the fun stuff.
Disappointing.
Okay, so tonight's lab is a continuation. This is the last chance to get the homework assignment done for the floating point conversion thing. So if you're done with that one already, there's really nothing to do. The next homework assignment is going to be a little bit fun because we're going to build on top of this circuitry so that we can use a 7-segment display to show 0 to 9. Whoa.
Okay.
Why is it changing to numbers? It's going 1 through 9, then A, B, C, D, E. Oh, it's a
in
bit 8.
hexadecimal
Big bit.
because it's in hexadecimal.
That's right.
So the content or the value of a register is reflected in hexadecimal.
Huh.
Yep. So are we good so far?
It's assembly.
Should we build this at home now, just for fun?
I think you can build it and just play with it, right? I mean, it's kind of cool. I mean, this is the first time we actually get to play with a memory device hooked up to an adder, and this is the simplest thing you can build is just a counter.
You just run it in the
Could we
library.
hook our adder up to that?
Yes, but your adder is only 3-bit, so that means the
Smaller range.
yeah, you just have to change all the width of the wires to only 3-bit wide. That's all. But you also have to specify the register to be a 3-bit register. But other than that, yeah, absolutely, absolutely. Yep. The timer may sound like a really simple device, but it provides the basic timing to your processor. This is how your processor can keep track of time. And all the multitasking stuff, all the threading stuff, they're all based on timers. So this is actually a very important, even though simple device inside the processor. All right, cool. So I'll see some of you tonight if you need to finish your homework assignment, and I'll see the rest of you next Monday. So try to read up, at least to finish the entire D flip-flop discussion before Monday, and then on Monday we will start on the actual processor design stuff, which is really fun.
Did we not get through the whole thing?
Huh?
Did we not get through the whole thing?
We got through the whole thing, but you should read through the whole thing too, just in case I missed something in my notes. Yep, there you go.
Thank you.
Down to the ring without it.